Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello, welcome back to another episode of the A-Level Cookbook. Today we're going to be going through AQA A-Level Chemistry Papers 2 from June 2022. So if we look at the first, an acidified solution of butanone reacts with iodine as shown below. Draw the displayed formula for CH3, CH2, CO, CH2I and give the name of this thing. So just start by looking at it and drawing it step by step. So displayed means you've got to show all the bonds. We've got a CH3 here. Next to it is a CH2. We have got a CO and then a CH2I. So if we just put the O here now for it's on its own, let's look at the rest. So CH2 and then an I like that. This carbon must have another bond, so it's C double bond O like that. So now we need to name this. So 1, 2, 3, 4. So it's going to be butan something. So butan. Now, you should be able to recognize that this is a C double bond O. So it's either your options are aldehyde or ketone. It's a ketone because it's in the middle. And also, aldehydes always have COH like that, and that's not what this is. So this one's got to be a ketone. So it's on the 1, 2, second carbon. So 2 own. And then we have an iodine as well. Where's the iodine? It's on the first carbon. So 1 iodo, butan 2. The rate equation for the reaction is rate equals K times the concentration of CH3, CH2, CO, CH3, and then H+. And then table 1 shows the initial concentrations used in an experiment. The initial rate of this experiment is this. Calculate the initial value of the rate constant K for it and give its units. So generally speaking, don't put the numbers in straight away. Rearrange the formula first, then put the numbers in, because if you've got an examiner who's marked like 2 million papers, they're not going to look through your scrawly handwriting and miss, incorrect numbers to try and give you method marks. Like, just don't chance it. So rate equals this whole thing. So that means if I'm going to rearrange this to get K, we need to divide it by this and divide it by this. So that means that rate divided by the concentration of CH3, blah, 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 and H plus is going to equal K. So they've given you the concentrations. And yeah, so in order to work out K, it would be the initial rate, so 1.45 times 10 to the minus 4, divided by the CH3 concentration, 4.35, times the H plus, which is 0.825. If we do that, we should get 1.45 times 10 to the minus 4 over 4.35 times 0.825. We should get 4.04 times 10 to the minus 5. So 0.4 times 10 to the minus 5. We need to work out its units. So if you look at the units, we're dealing with mole dm minus 3 s minus 1. And we're dealing with what? Mole dm minus 3, mole dm minus 3. So if we rewrite that, that's going to be mole dm minus 3 s minus 1 over mole squared dm minus 6. Because when you times it together like this, you're adding the indices. If you're dividing, you're subtracting the indices, which is what we're doing here, because we're dividing now. This mole is dividing by its here, so this is mole to the 1 divided by mole squared, so you're going to get mole minus 1. And then we've got dm cubed divided by dm6, so 3 minus 6, so that's going to be 3 plus 6, which is dm cubed, and then this s to minus 1 isn't divided by anything, so it's s. Now it says, calculate the initial rate of reaction when all of the initial concentrations are halved. So they've given you the rate equation. They told you rate is K times the whole thing. So rate is proportional to the C blah, 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 and then the H plus, right? So they've told you that if you're halving every single initial concentration, you're timesing this by a half. So that means the rate would also times by a half because it's first order with respect to this. But then as well as that, this is also being times by a half. So then you times this extra by a half. So then all you've got is you've just got your rate times a quarter, which is going to be the one they've given you, the 1.45 times 10 to the minus 4 times a quarter, or divided by 4. If you do that, 1.45 times 10 to the minus 4 gives you 3.625 times 10 to the minus 5, which is roughly, 3.63 times 10 to the minus 5. An experiment was done to measure the time taken T for a solution of iodine to react completely when added to an excess of acidified solution of butanone. Suggest an observation to judge when all the iodine had reacted. So we're adding iodine. Iodine is like a brown sort of solution, like when it's added. So if it's all reacting, then generally speaking, that's forming like I minus ions. So the brown color's gone because it's not I2 anymore. Removed, or it disappears, or it It's gone. So now it says the experiment was repeated at different temperatures, and then figure 1 shows how 1 over t varies with temperature for these experiments. So 1 over t is like a rate in itself. So describe and explain the shape of the graph shown in figure 1. So first of all, let's start off with describing it. So as the temperature climbs up, yes, the 1 over t goes up as well. But if it was that, if we just left it like that, it would be this, like a straight line. But you can see that it's sort of bending like that. Generally speaking, when you're comparing graphs like this, the steepness of the line is the gradient, and that tells you how much this is changing with this. Because if that's flat, the gradient is flat, the steepness is 0, so it's not changing very much. Whereas if it's like this, the steepness is near infinite, as in it's changing like crazy. So if we look here, it's barely going up. It's kind of going up faster because you can see they've got that much of an increase from 10 to 25, and now it's like that. And then it's like this, and it's even more steep. So that means that as it's going on, the amount it increases gets steeper and steeper, and that's called an exponential relationship. So as t increases, 1 over t increases exponentially. Right? So that's described, but we need to explain why. So any thoughts? Well, we know that rate equals k times the concentration of whatever and the concentration of the other thing, right? Now, you should be able to recognize, well, actually, you tell me, what are the two things that any reaction needs to take place? Absolute bare minimum things. Have a sector thing. Right. So for any reaction to take place, the two particles, or three or however many, need to react by colliding with each other in the right orientation, but not just that, they also need to have the activation energy to react. So the collisions and enough activation energy. This equation on its own doesn't say T or activation energy in it, so it doesn't factor that in, but it does because rate, well, it doesn't explain that, it doesn't directly get changed. If you change if you change the temperature or activation energy, these don't change. The only thing that must is K. And if you think about it, well, you should think, okay, what does links K with activation energy and T? AE minus EA over RT. That's the whole point. That's what that is. So it's just important to make that link. So here, back to what I was saying, if we're increasing the temperature, 1 over T, the rate is going up, like exponentially. And that now makes sense because K is related to, well, E to the minus EA over RT. So if you're increasing the temperature, it shows in this equation, obviously you've got to turn it into words. It must mean that many more particles have energy that's greater than the activation energy, or energy sufficient enough to react. So now it says, deduce the time taken for the reaction at 35 degrees Celsius. So just look at the graph and see what's going on. So 35, 1 over t is going to be 0.03. So then the time is going to be 1 over 0.03, which is 33 seconds. Done. Next, it says, for a different reaction, table 2 shows the values of the rate constant at different temperatures. So we've got an experiment 1, we've got a temperature of this, and we've got the rate constant here. This equation can be used to calculate the activation energy. So ln k1 over k2 equals EA over R, 1 over t2 minus 1 over EA. Sorry, 1 over t2 minus 1 over t1. It says calculate the value in kilojoules per mole of the activation energy. So again, don't try and do anything like, mucking about with this yet. Just rearrange it first. Otherwise, you're going to just struggle. So ln k1 over k2 equals EA over R times 1 over t2 minus 1 over t1. So look, we want to get to EA. First thing we could do is times both sides by R. So R ln k1 over k2 equals EA times 1 over t2 minus 1 over t1. That's a 1. Right? And now this EA is multiplied to this. So to get EA on its own, EA would equal R ln k1 over k2 all divided by 1 over t2 minus 1 over t1. Now, we can just put the numbers in because now it looks very clear what we're doing. We're going to get those method marks. So then that would give us 8.31 times ln and then k1 over k2, which is 1.55 times 10 to the minus 5, yeah, k1 over k2, over 1.7 times 10 to the minus 4, all divided by 1 over the second temperature, 333 minus 1 over 303. If you put that in your calculator, you should get 66936.7, which is, well, remember, we need to look at what this actually relates to. This is activation energy. And when we're using these activation energies here, can you see that that's joules per Kelvin per mole? This one has to be in moles. Or sorry, joules per mole. Whoops. So if we're doing it so if that's in joules per mole, then to get it to kilojoules per mole, you got to divide it by 1,000, which is 66.9 kilojoules per mole. Name and outline the mechanism of the reaction of butanone with KCN followed by adding, dilute acid. So we've got butanone, that's a ketone, and we're adding it with KCN. Well, what part of this is going to be reacting? It's going to be doing the CN minus part, right? You should be able to recognize what that does by thinking of the big flow chart in your head. So if you're reacting a ketone and KCN, you're going to be making a hydroxynitrile. So think about what's going on here. You've got the C11O, because that's what all ketones look like, and all hydroxynitriles would be COHCN, like that. If you can recognize what each of the groups look like, then it makes it a lot easier, because then you can describe what's happening. To go from here to here, what you've done is you've added an H here, and you've added a CN here. So we know that this is a addition reaction. So then, what's doing the adding? What's being added on? So we need to think, why is this going for the ketone? Well, it's got a lone pair of electrons, and it's forming a bond here like that. So it's something that wants to go for electron deficient things. It wants to give away its electron pairs. An electron pair donor, as everyone loves to just say, but not actually understand. So it's nucleophilic addition. So you could sit and memorize it. You can take a second just to realize, oh, that's what's going on. So you're adding this on, along with an H, and it's attacking this carbon that's got an electron, that's electron deficient. So then outlining the mechanism becomes a lot easier as well, because then you can just, it doesn't take as much mental strength now, because you can just think about it step by step. So if you look at what's going on, we've got butanones. It's going to be 4 carbons. I'm just going to be lazy and do this. You write the whole thing, obviously. CH3, CH2, C double bond O, and then a CH3. It's butanone. So if it got in here, then it would obviously still be the same thing. And you can't have the double bond O there, because that would make an aldehyde, because it's on the end. So this is your butanone. And then it's the CN minus that's doing the interesting part of the reacting. So the way to think of this is to describe it in terms of electron pair movement, and then it makes a lot more sense. Don't just memorize where the arrow's going from and to and so on and forth. Be able to actually explain it. So this thing is giving electron pairs away to this other thing. So direct consequences. Don't just say, oh, an electron pair is donated from what to what, right? So this thing wants to bind somewhere on this carbon. Now, because this carbon's bonded to an oxygen here, this carbon is slightly positive, that's slightly negative, because of differences in electronegativity. This oxygen is more electronegative, so it's going to drag the lone pairs of electrons, the bonding pairs of electrons here to itself. So because that's slightly positive, this electron pair specifically is going to be drawn to this carbon. So what it does is it donates its electron pair to carbon like that. That's the nucleophilic addition part. However, if we do that, that's saying a bond has been made here. So now we've got 1, 2, 3, 4, 5 bonds around the carbon. So carbon's got too many. So what it needs to do is it needs to boot something off, because it can't have 5 bonds. Now, it's not going to boot off what just reacted with it, because that's what's most happy. So we need to think what's it going to boot off. So I don't know if this is technically true. This is just something that I kind of made up, and it helps make sense. It tends to boot off the most electronegative or the most electron-rich thing, generally. So if we look between this carbon and this carbon, or the other carbon before it, they both have similar electronegativities. So their electron pairs are going to be kind of like slap bang in the middle. Whereas this oxygen has it's more electronegative. So the electron pairs that are already there, I know there's 2, but I'll just draw 1, is more close to the oxygen itself, and there's lots of electrons there too. So when you add these extra electrons, like magnets almost, it's pushing them even further that way, until eventually they just all get they just get straight up passed onto the oxygen itself, so far away from the carbon. So what happens is this bond breaks and a lone pair goes that way. So double-headed arrow means 2 electrons. If you think of it like that, it makes a lot more sense, because now you actually understand what's going on. So in your next step, what you end up with is you've got CH3, CH2, CCN, that's just joined on here, remember? The CH3s like so, and then you've got your it's now got a lone pair of electrons, and it's negative. These things don't like to just chill like this. It needs to sort of resolve the problem here. So you need to think about what's going to happen next. Well, this lone pair of electrons has to go somewhere to make oxygen back to being itself and happy. And also, as well as that, we've established that it's going to make a hydroxynitrile. So we've got the nitrile part there, but we don't have the hydroxy. The hydroxy means OH, so it'd be an H here somewhere. So what actually happens is an H plus is here as well, and you need to figure out which way the electrons are going. So H plus means there's no electrons in its outer shell. This has extra electrons to give away, so it donates its electrons to the H like that. And it makes sense where this H plus comes from because acids are H pluses. When you add acid, you're adding H plus, and they've told you it's got dilute acid, so you are adding the H pluses through that. So then overall, the entire thing would be the atom product, which is just CH3, CH2, C double bond O, CN, which the arrow is not there, and then, sorry, C double, not C double bond O, COH, and then CN, and then the CH3 like that. So when you're learning these mechanisms, actually know what an electrophile does in your own words, be able to describe it, and also what a nucleophile does, and also what's happening in terms of electron pair movements, because then you can do it with any scenario, even if they give you an unfamiliar molecule. Sometimes they do give you unfamiliar mechanisms that you've never covered and never expected to cover and tell you to do it. So it's really important to be able to describe what's going on. So tetrafluoroethene is made by reacting chlorodifluoromethane in this reversible reaction. So we've got this going to this. And they've told you that the enthalpy change of the forward reaction is plus 128 kilojoules per mole. So a 2-mole sample of CHClF2 is placed in a container of a volume of this and heated. When equilibrium is reached, the mixture contains that many moles of CHClF2. Calculate the amount in moles of C2F4 and HCl in the equilibrium mixture. So don't just like calculate random stuff for the sake of it. Think of what's going on. What they've done is they have mixed this much. Sorry, not even mixed. It's just they just got 2 moles of that thing and left it. And over time, eventually, these two will have appeared. So obviously this must have dropped for these to appear because all of these must come from there. So when doing these kinds of questions, you do C2CHClF2, reversible reaction, C2F4 plus 2HCl. And then what you do is you write your initial moles, like, you know, right before at the start when things are happening, and then your equilibrium moles or your end moles. That's how all equilibria behave. So at the start, what have they done? They've reacted 2 moles. Well, not reacted. They just put 2 moles of this stuff. So I'll just write 2 just because I've written moles there. So 2. How many of this do we have? Well, it's at the very start. We have none because it's not actually started doing this yet. And then in the equilibrium moles, well, what have they told you? That they've told you that when equilibrium is reached, you have a mixture of, you have that much CHClF2 left at the equilibrium, so 0.270. So whatever this decrease must have been has had to have gone into making those. So if we do 2 minus 0.270, this has dropped by 1.73 like that. So if 2 moles of this has dropped by 1.73, these 2 moles dropping, the 2 of lots of them, sorry, will end up making 1 lot of this and then 2 lots of that. So this must have gone up by 1.73 over 2 because it's a 2 to 1. Every 2 of these that, decompose or whatever's going on here makes 1 of them. And then as well as that, this, because they're in the same ratio, must have gone up by 1.73. So at equilibrium, the amount of HCl we've got is 1.73, and then for the C2F4, it's 0.865, and that's that. So 0.865, and then 1.73. So again, it's just thinking about the steps, what you're doing. Don't follow routines. Say, why am I doing this? What's the purpose? And then it says, write in a Kc for this equilibrium. So again, it's just looking at the products and the reactants. So Kc is going to equal, well, it's going to be the concentration of C2F4, because it's Kc they want, and HCl squared, because there's 2 moles of it, all over the original thing, which is, what's that? CHClF2 squared. They don't want partial pressures. It's told you it's Kc, so you've got to use concentration. Now it says calculate a value for Kc and give its units. So just for the sake of it being here for this question, I'm just going to rewrite it. So C2F4 concentration, HCl concentration squared, all over CHCl F2 squared concentration. So we need to put the numbers in. So we've got the moles of everything at equilibrium, but not its concentration. So if we go back here, we've got our equilibrium moles. Let's work out our equilibrium concentrations. So remember that N equals CV, so C equals N over V. And they've told you the volume here. So these concentrations must be, well, 0.270 divided by 23.2 and so forth. So the moles of every single thing should be 0.270 divided by 23.2, which gives you, because it's already in decimeters cubed, that's very nice of them, 0.01164. And then for this one, it's going to be the 0.865 divided by the volume. So 0.865 divided by that, which gives you what, 0.30373. And then the 1.73 divided by the volume, which is 0.07456. Well, sorry, 7. Let's go with that. So then, to work out Kc, all you do is you just plot the numbers that you've now worked in, because these are concentrations. So C2F4, it's going to be 0.0373 times the HCl squared, which is going to be 0.07457 squared, all divided by the CHClF2 squared. So 0.01164 squared. So if I do that, we get 0.0373, then 0.07457 squared all over 0.01164 all squared. So if we do that, we should get an answer of 1.53, because we want to match the significant figures of the question. And as well as that, we need to work out its units. So if we look at the units, it's going to be moles per decimeter cubed times moles per decimeter cubed squared all over moles per decimeter cubed squared. So do it like this and then start like multiplying that. Because you can see straight off the bat that cancels out, that cancels out. All left is moles per decimeter cubed. Done. Because what I see is some people will be able to start combining them straight away as they go along. So they've got moles squared dm, -6, but then it's also another one. So it's just confusing. Like just do it like that first. And you might spot an easy cancellation-y outy bit. So again, don't follow routines. Look at what the question's telling you at face value. Because a lot of people I've seen, they'll just sort of look at it and be like, oh, it's gases, it must be Kp, and they get it wrong. It says Kc, it's got to be concentrations. So the next question, to actually calculate, you need concentration. So you need to look, where do I get concentration from? Well, they've told you the volume here in decimeters cubed. There you go. So now it says, state and explain the effect of using a higher temperature on the equilibrium yield of tetrafluoroethene. So as in this, it's told you that the forward reaction is endothermic because it's a +128. So if you increase the temperature, then the yield increases, right? So the explanation why, well, increasing the temperature means equilibrium shifts to the left, but that doesn't the shift to the left to counteract the temperature increase. You need to say by how, because that doesn't tell us how. By moving in the endothermic direction to absorb the extra heat. So it does seem a bit excessive writing that, but it just guarantees the marks every single time. Because sometimes it'll say, oh, do you know, counteract the change, blah, blah, blah. Just say it off the bat. You know, it's moving to the left or the right. Why? To counteract whatever change you made. How? By moving in the endothermic direction to absorb more, extra heat. Or for example, if we increase the pressure, then it'd move to the side with fewer moles like that. Why? And how? So the reason is to balance out the pressure again, to counteract the increase in pressure. And how these two react together. So C2F4 will react with HCl. You got to say the hows, and it'll always get you the marks. Even if the mark scheme doesn't say it and it's nice and friendly, this one expects you to say moves in the endothermic direction and so forth. So just do it by default, because you want to cover your grounds. So chemists provided evidence that was used to support a ban on the use of chloro-difluoromethane as a refrigerant. Many refrigerants now use pentane instead. State the environmental problem that chloro-difluoromethane can cause, and then give one reason why pentane doesn't cause this problem. Well, it's because that this is a chlorofluorocarbon, so it causes ozone depletion. And then reason why. So think, why do chlorofluorocarbons cause ozone depletion? It's because they can form do things with free radicals and stuff. Why? Because that's CCl bond. So the reason pentane doesn't do it is because pentane doesn't have CCl bond. So it doesn't make chlorine radicals, so it can't do all the rest of the stuff. This question's about 2-methylbutanone. Name the mechanism of the reaction with concentrated sulfuric acid, and then outline the mechanism that forms the major product. So you should be able to recognize that, first of all, this is an alkene, and you're adding concentrated sulfuric acid. So if you add an alkene to concentrated sulfuric acid, it literally sticks the sulfuric acid bit onto the molecule. But if you then add water, it makes the alkene become an alcohol. So what's happening, generally speaking, is you're going from an alkene to an alcohol. How? By doing the sulfuric acid plus the water. Now you've got to look very superficially in the question. It does not say anything about it being diluted or any water, so there is, in this case, no water present. So then let's think about what's going on. So you've got an alkene, we're adding the H2SO4 stuff on it, so the reaction's got to be addition. Now we need to figure out what the sulfuric acid bit is behaving as. Is it a nucleophile, an electrophile? Is it a radical, free radical? So alkene to alcohol eventually, the double bond is gone. So that double bond has to go somewhere, so it must mean the electrons in that double bond have gone to something. So if something is taking electrons from a double bond. It's accepting them, meaning it has to be electrophilic addition. So now if we draw the mechanism, what's going on here? So it's told you you've got 2-methyl bute 1-ene. So 1, 2, because it's bute 1. 3, and I've got our H's here. All right. So that's our first bit. But now we need to figure out what part of the H2SO4 is actually doing the reacting part. So H2SO4 looks like this. We've got HO bonded to an S and an O and an H. And then sulfur needs the other bonds there, the other two. So it's going to, sorry, the 1, 2, 3, 4, 5, 6. So we're going to need 2 more double bonds here. So 2 O's. If it wasn't for the H's, then in theory, they would just be double bond O's and all around. So that's how I remember it. So we need to figure out what part of it is actually acting, in this reaction. So this C double bond C, what it does is it mucks about with something. So you guys should remember, like in BR and BR, it's chilling, but then eventually that becomes slightly positive, or slightly negative because of this stuff, right? That double bond induces a dipole between these two. So in the same sense, you need to find where the dipole is being induced. It's not going to be here because that's pretty stable. It's going to be here because this hydrogen is slightly positive, that oxygen is slightly negative. So remember that because this oxygen is one electronegative and also because it's a hydrogen bond, the electrons are like really close to oxygen like that in the covalent bond. And these like really rich electrons in the double bond are going to repel that even further, almost like nearly pushing it entirely onto here, is how I make sense of it. So what happens is, because these are repelling so hard and so like pushing on those electrons essentially get passed on to the oxygen like that. This hydrogen doesn't want to be bondless, so what happens is a pair of electrons from the double bond go to that hydrogen, right? So then what you're left with is so the double bond's now gone, and you need to figure out what the major product is. So the major product is going to be the one with more alkyl groups on. Why? Again, not sure if it's like technically correct, but this is how it makes sense to me. If we look here, it could go in this carbon or it could go in this one. If we look at this one, it's only got like, those electron pairs there alongside this. Whereas here, you've got like this, and then all of these electrons here, and then all of these electrons here, which add to this just like pushing electrons this way. Like it's repulsion more, is how I make sense of it. So that's kind of why that's the major product. So that means that this first one's going to nab that hydrogen, and this second one is going to form your carbocation, remember, because there's no bonding that's actually happened between this stuff yet. So we've got a carbocation chilling here, so CH3, CH2, CH3, right? And then the other thing, and it's also made, well, now this oxygen's accepted those electrons, so it's going to be your S, your O, and your H here, your O with 2 electrons here, and then a double bond O, and a double bond O. Then, well, so that's a plus is in like adding this with this as well. This, in your normal electrophilic addition reactions, this actually then donates its electron pairs like that. So when it's donating its electron pairs, it's acting as a nucleophile. So electrophilic addition has a bit of both. So then what happens is it literally, draw an arrow like here, a bit better than that, and it sticks on there. So you've got an H, C, H, H, C, H3, CH2, CH3, and then you've got your O, which is there, the S, the O, the H, double bond O, the double bond O. Like that. And that's it. Because they don't want you to go any further, because we haven't added any water yet. Once this reaction part's over, you can add water, and that will swap with, so that'll take this off and then put an OH in its place. But we're not doing that because I told you it's concentrated sulfuric acid. The question would tell you it's dilute. So the minor product is going to be H2CO, and then the whole SO4 bit. So I'm just going to draw it like this, write it out like this. You can do displayed formula, it's fine. CH3, H, CH2, CH3. And then it says explain why. Well, the major product is formed due to the more stable tertiary carbocation versus primary. Because if you look, it's tertiary because it's carbon here, and then another one there, and another one there. So that's 3 of them versus just 1. This is only bonded to another carbon. And then that doesn't explain why, though. The why is because those alkyl groups can either demonstrate the positive inductive effect, or you could even paraphrase it. You could say that it feeds electrons towards the positive charge. And there you go. Or you could say like electron releasing character and all these other things, but that's what it's the point. So if you think about, again, movements of electron pairs and stuff, it makes it a lot more easy to do. So if you notice, the pattern I'm following is what marks the start of whatever it is we're dealing with, what marks its finish, and then what the overall thing is, and then the how, the actual steps in between. If you do it like that, it makes it a lot easier. And a lot of the time you can do it with just by looking at what the content in the question says. It says, draw the skeletal formula of a functional group isomer of 2-methyl-bute-1-ene. So I'm just going to quickly sketch this out. So 1, 2, 3, 4, bute-1-ene, and it's a 2-methyl here. So if we look at that, it's got to be 5 carbon, C5, and it's an alkene, so it's C5H10. So it's literally just any, when you have alkenes, just kind of a fact that you pick up over time, to be honest. Whenever you have an alkene, a skeletal formula or a functional group isomer could be cycloalkanes, generally speaking, because if CnH2n plus 2 is for alkanes, alkenes is CnH2n. If you're forming a cycloalkane, in order to do that, you have to knock off 2 hydrogens, so you end up getting CnH2n. So functional group, remember, is the thing that's actually interesting about it. So in an alkene, the functional group is the CC. The functional group of a cycloalkane is the fact that it's an alkane in a circle. So 1, 2, 3. Oh, dang it. 1, 2, 3, 4, 5. That'll do it. There you go. So 2-methyl-bute-1-ene conformal polymer, state the type of polymerization, and then state the repeating unit. So the only ones that you guys know about is condensation polymerization, in which H2O is released, and addition. Addition is the one that alkenes do. So addition. And you can tell because there's also no H2O to release or a small molecule. So then it's addition polymer, so just draw what it is. So it's bute-1-ene. So if we drew it like actually, so if we actually drew it out, if I'm just going to quickly sketch this, so 1, 2, and there's 2-methyl like that. So then you just pick the double bond bit and open it up. So the C double bond here with its CH3. I should have written CH3 there, sorry. And then it's the other stuff. So the CH2, CH3 there, and the double bond opens up. And you've got your... So proteins are polymers made from amino acids. Part of the structure of protein is shown here. So cis, ser, asp, phi. And it says each of the amino acids in the protein is shown using the first 3 letters. So what type of structure is it? Well, it's told you the amino acid sequence, it's primary. Draw a structure for the cis-ser section of... It says draw a structure for the cis-ser section of this protein. And it says use the data booklet to help you with your answers. So we're looking at cysteine and serine, because it's told you it's the 3 first letters, it's these 2. All amino acids in the universe follow a C and H, an R group, and then like a carboxyl group here, and then an H2N here. You should be able to recognize the bond between them. So a peptide bond and amide link are the same thing. So every single one of them, you should see there's a C double bond O and an NH like this next to each other. All right? You should be able to recognize that off the bat. So what's happening if you've got cis and ser is that between them, they're going to have this. So what I do is I just pick cysteine. So that's going to be this one here. And then I draw it. So it's a CH. And its R group is a CH3SH. We know it's going to have a C double bond O, and then next to it, an NH. But remember, this has got its own NH2 here, but it wants a singular, so it's going to be a H here. The other H isn't going to be there because it's bonded with the other C double bond O from a preceding one. So it's going to be a line drawing out that way because we're only drawing, it just wants you to draw this section of it. So that's the cysteine part, and then the NH on the other side is from the next amino acid, which is serine. So that's going to be NH, and then a CH, and then a CH2OH, and then a C double bond O, and then the NH of the next one. So it's just recognizing that. But the reason we don't do a C double bond OOH is because it wants a section. Remember that these are going to be bonded onto the next things as well. If it was just this, it was a dimer of these two, then you could put the NH2 here and the C double bond OH, but it's not. And you can see, actually, when you recognize the C double bond O and the NH, you can see that the H and the OH from this side combine to give you that water that's released. So just, again, like, look at the... So then it says, name the other substance formed when they react together to form part of a protein chain. It's actually water. There you go. Bingo. So then it says, R represents a group that varies between different amino acids. R groups can interact and contribute to protein structure. Explain why the strength of the interaction between 2 cysteine groups differs from the strengths between the interaction between a serine R and an aspartic acid R group. So if we look at cysteine to cysteine, what, like, as in we're interacting between the two of them, what have we got? Well, you can see cysteine as an SH. So off the bat, you should be able to recognize it can form a disulfide bridge. And as well as that, it's got its H, it's got its NH as well, and so that means it can form hydrogen bonds. And remember that just like in when it's bonded as well in itself, it's not going to have that OH again there. So C double bond O, remember, isn't a It isn't a hydrogen bond. Now, if you look at serine, or what was it? Aspartic acid. Remember, these are the interactions between them, not them bonded to each other. So remember that this isn't them bonded to each other, it's just the interactions between them in two molecules. So I mean, like in a molecule. So for example, there might be a serine here and the aspartic acid here, for example. Or it could be like a cysteine and a cysteine here is what I'm trying to get at. So if we're looking at serine and aspartic acid, the R groups of them are CH2OH, and the OH is there. So here, this is hydrogen bonds. So you should be able to, you should look at this and think, what's the key differences between these two, and why is this one stronger? So the thing that's giving them that, it must be the disulfide bridges. So the cis R groups, the two of them, form disulfide, I'm going to disulfide short, bridges, right? Whereas the CYR and the ASP, well, they produce hydrogen bonds. That's what holds them together. So then, disulf must be stronger than hydrogen bonds. That's the only difference between them. And you need to explain why. What's the difference between disulfide bridges and hydrogen bonds? Well, disulfide bridges, remember that this is where you got an SH and another SH coming along, and those H's are gone, and it actually becomes SS. What's the difference between that and a hydrogen bond? So OH, it's those sort of interactions between molecules, right, intermolecular force. So the reason it's stronger is because this is an actual covalent bond. These are physically sharing a lone pair of electrons versus an intermolecular force. And that's why it's stronger. Okay, so sorry if from this point on I sound a bit funky. I had a dental procedure done, and my face is a bit numb and a bit droopy. So, yeah. Okay, so moving forwards then, it says deduce the type of interaction that would happen between the lysine R group and an aspartic acid R group. So if we look at lysine, it's got an R group of CH2, 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 NH2, and then it's aspartic acid. If we look at that, its R group is CH2COH. So we've got an amine and a carboxylic acid. We need to think what kind of interaction would happen between those two. Any thoughts? Well, if we look at the aspartic acid, that's a carboxylic acid group, so that is a COOH. And if you guys should know that carboxylic acids are proton donors, which means it can become COO minus. If that's a COO minus and there's an H plus, that H plus can be accepted by the NH2 there, the amine group. It can act as a base, a proton acceptor, an H plus acceptor. So when you've got oppositely charged ions bonding with each other, that is an ionic bond. This question is about the preparation of hexane 2-ol. Hexane 2-ol does not mix with water and has a boiling point of 140 degrees Celsius. It can be prepared from hex-1-ene by doing this method. So you get 11 centimeters cubed of hex-1-ene in a boiling tube in an ice bath. You add 5 centimeters cubed of concentrated phosphoric acid to the hex-1-ene. After 5 minutes, you add 10 centimeters cubed of distilled water to the mixture and transfer the boiling tube to the contents of the separating funnel, and you shake the mixture, allow it to settle, discard the lower aqueous layer, add a 10 centimeters cubed sample of distilled water, and repeat steps D&A. You transfer the remaining liquid to a beaker, and then you add 2 grams of anhydrous magnesium sulfate, and you allow it to stand for 5 minutes. Then what you do is you filter it under reduced pressure as well, and then distill the filtrate and collect the distillate that boils at that. It is important to wear eye protection and a lab coat when doing this experiment. Suggest with a reason, one other than appropriate safety precautions. So, well, what do we think is going on? Why on earth would you need to wear eye protection? Obviously, everyone does it by general, but they're asking specifically what's going on in this scenario to make that happen. Well, if you look, it's what they're trying to get at is you need to look at the experiment, think what in the experiment specifically warrants these things. So, another say, so for example, because we're dealing with organic compounds, we want to keep them away from a naked flame because they're flammable. Or alternatively, what we doing? We are boiling stuff into like distilling, so we don't really want to inhale that, so do it in a fume cupboard. Alternatively, we are dealing with concentrated phosphoric acid, so you should wear gloves as well. Or what else? We're using a separating funnel to separate this stuff as well here. So, and this. So you don't want the pressure to build up too high, or it will blow up. So any of them. So I'm going to go with the keep away from naked flames. So keep away from naked flames. And why? Because organic compounds are flammable. Then it says, give a reason for adding the distilled water in step C and F. So if we look, they want you to make hexan 2-ol, and it does not mix with water. So they're adding the water, it ain't going to mix with this, but it's going to get rid of all the other junk that's been added here, all the other stuff that will be taken away with the water. So what it does is, the reason we do this is to remove water soluble impurities, because what that means is we've got this, if we got the separating funnel here and stuff, and we've got our, our aqueous layer here and then the actual organic layer there, then all of this is going to be stuff that don't dissolve in water. So the hexan, whatever we're making, sorry, hexan 2-ol. Whereas all the water and anything that dissolves in water will be here, so it all gets passed out together like that. So that's why we do it. Why do they add the anhydrous magnesium sulfate in step H? Well, it's to just get rid of the extra water we've added, so it's to remove water, because when you're separating them with a separator funnel, you don't know that you've guaranteed removed every single bit of that of the aqueous layer in the water. Next, it says complete the diagram of the apparatus used to filter the mixture under reduced pressure in step 1. So you've got a Buchner flask and it's to a vacuum pump. What we need is we're going to need a funnel going into this. We're also going to have to, I should have drawn this a bit better, close it off with a bung as well, but not all the way. We only want to seal the sides here so that it's all been drawn down. And then what we want is a layer of filter paper as well, like so. And then you would label this saying filter paper, and then you would say this is a, and then you would say that's, or a collar or whatever you want. So then it says identify the most likely organic impurity other than hex 1 in the distillate can collect it in step J, and suggest why it might be difficult. So again, we're looking at what we got. We've got a hexan 2-ol, and they're using, so that what they're doing is they've got hex 1 ene, and we're going to hexan 2-ol, right? Now you need to be able to recognize that that's an alkene, and we're going to an alcohol. So you should be able to recognize that this is the reaction with steam and water and stuff to make an alcohol. So the thing is, though, is that if we look at just the alkene group carbons here, we don't know if it's going to go on this one, or if we don't know if it's going to be on this one, right? And that's what the other impurity is. The other impurity has to be the other alcohol that we don't want, which the other possibility could be it was on this carbon versus that one, so hexan 1-ol. Hexan 1. Oh, now it says, suggest why it'd be difficult to remove this impurity. So you need to figure out how they're actually removing that impurity in this step. So again, just like hexan 2-ol, it's not going to dissolve in water, so it's not going to be doing the separating funnel part that they're separating it. The separating funnel bit is to get rid of all the aqueous stuff. The distillation is to boil off the other stuff. Now, if we look at like hexan 1-ol and hexan 2-ol and distilling it, it's probably going to be really hard. Why? Because they probably have similar boiling points to hexan 2-ol. Because what we're doing is we're separating them based on boiling points, and if these are both, alcohols like this, and they're both the same carbon length and so forth, probably going to have a similar boiling point. So then it says, calculate the mass in grams of hexan 2-ol formed from 11 centimeters cubed of hex 1-ene if the yield is 31%, and give your answer to that, and here's the density. So a lot of people just look at this and they're like, what formula do I use? Oh no! So a lot of the time people look at this and like, all right, what formula do I got to use, bro? I got to just work out the mass of everything and moles of this and that and blah, blah, blah. Like, step by step, whenever you work out a mass or a moles, you need to know what you're doing it for, why. So they want us to find the mass of hexan 2-ol, and they've told us that the yield of this stuff is 31%, and they've given us the density. Step 1, figure out what the hell the actual reaction is. So you've got hex 1-ene, and it's doing all of its things with its water and its phosphoric acid and so forth until you get hexan 2-ol. Make sure you're balancing this. So this is because we're changing, we're only going from like alkene to one of these. It's one alcohol group being added, and there's only one alkene group here. It's going to be 1-to-1. Right? Now, they've told you that you have 11 centimeters cubed of hex 1-ene. So here we have 11 centimeters cubed of that. In order to be able to get to a mass here, we're probably going to have to do some of that mole messing around stuff. So you're like, dang, how am I supposed to find the moles of anything here without this information? Well, that's what this bit here has told you. They've told you that the density of it, of hex 1-ene, this thing here, which is why it's important to know what you're starting and finishing with, is 0.7678 grams per centimeter cubed. So if we can get it to grams, then we can then work out the moles and then do some molar ratio-y stuff. So the way to get rid of the centimeters cubed is because this is a per centimeters cubed. What that means is it's a something in grams divided by something in centimeters cubed. You times it by something in centimeters cubed. That relates to this. As in, you can't just do, like, for example, they gave you a volume of that, you can't do it. It has to be a volume of this. And they've told you that there. So therefore, and write this down, the mass, and then what it is you're working out, the mass of what, otherwise you don't know what you're doing, equals this volume, 11 centimeters cubed, times its density, which is 0.678. That should give you 7.46 grams, right? So now we know what the mass of this hexagonine is. Next, we can find its moles, and then we can find the moles of this and so forth. So if we work out the MR of hexagonine, we need to draw it real quick. So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. And it's hexagonine, so it's going to be there, and then all the rest of them, so forth. Or you could just do CnH2n. Anyway, just to skip ahead, I'll tell you that the MR here is 84. So that means that the moles of, and again, write what you're looking for, so it's a cue to yourself to know what you're doing, is 7.46 over 84, which is 0.0888 moles, right? And this is the moles of hexagonine, which is what we start with in this reaction. A lot of people get to this point and they don't know what they just worked out. They're like, what am I doing? So we have this many moles of this, therefore we expect that the moles of hexan 2ol is also should be 0.0888 moles. Therefore, the mass should be the moles here, so 0.0888 times the MR of hexan 2ol, the mass of the hexan 2ol. So it should be, I'll just tell you that the MR is 102, it should be that. So if we do that, we get 0.0888 times 102, which is 9.0576 grams. However, they've told you in the question that this reaction here, the percentage yield of it is 31%, as in the yield of that, which is why it's really important to understand what you start and finish with and how many moles you're going from and to. So that's what you should be getting. However, percentage yield is 31%. Therefore, the actual mass you get is going to be 31% of that theoretical yield. So it's going to be 0.31 times 9.0576, which gives you 2.8 grams. So it's really important to just think logically what you're doing and stop following routine. Okay, so the next one then, it says, this question is about compound X with the empirical formula. I'm just going to rewrite that, C2H4O. With these questions, you need to use these pieces of the puzzle step by step. You cannot just dive in. And with these, I recommend you write down every single step of your conclusion. If you can't figure out what the structure is within about maybe 2 minutes max, just leave it and move on. But at least write down the evidence that feeds you into what it could be. So now, it says figure 2 shows the infrared spectrum of X. And then figure 3 shows the carbon-13 NMR spectrum of this. And then the proton NMR spectrum of X shows 4 different peaks with chemical shift values, and table 3 gives you those values there. It says, show how the information of figure 2, figure 3, and table 3 can be used to deduce the compound of structure X. So you need to write down what evidence there is and what it could suggest for each thing to show them that you're thinking about it. So go through it bit by bit. I'll start by saying that we know off the bat its empirical formula is that, fine. Let's look at the infrared spectrum. So if we look at the IR spectrum, we want to find all the peaks that are of interest to us. So either go this way or that way, just work across systematically. So I usually go this way. If we look here, we can see that there is a broad peak at around, 3 to, if you look at the data sheet, 3,230 to 3,550. Try to say it specifically to this example. Don't just write what the datasheet shows. It doesn't show them that you're actually thinking about what this example's saying. So here, we have a broad peak. Now it's broad because it's like really thin here, whereas these are quite narrow. Broad peak at around 3,400 cm minus 1. And then you need to say what that indicates. So it suggests what? So it suggests an OH in an alcohol. That is what you need to do for like basically every step. So then if we look at the next IR piece of the puzzle, what else have we got in this? So let's see, what else we have. Nothing else. We've got something going on here. That looks a bit more exciting. That's what, 1,700? So we have a peak at 1700 cm minus 1. If we look at our data sheet, that suggests that it is a C double bond O. That's all we could get from that. Next, they've given us what? Figure 3? That's the carbon-13 NMR spectrum. So rule number 1, obvious stuff first, right? So if we have the carbon-13 NMR spectrum, we can see over here, we can see there's 1, 2, 3, 4 carbon environments. There's 4 peaks. So say that overall. Say the overall things first, then get into it. If I look at a chest X-ray of a patient, I ain't going to start looking at the nitty-gritty of every single part, because if there's a massive obvious thing, I'm going to look at that first and say, that's what I see, but I'm going to go and check everything else. So here, there are 4 peaks. So there must be 4 carbon environments. Then I work this way with those, so from 0 onwards, just because it makes a bit more sense. So if we look at what we got going on here, so in this carbon-13 NMR spectrum, we have a peak at roughly what? 25-ish. So 25, and that's roughly, roughly 25 ppm. So that suggests what? So if we look at our carbon-13 NMR spectrum, that's probably going to be, what are our options? It could be CC, it could be RCO, it could be a lot of different things basically. But I'm gonna just leave. I'm just so say what it suggests. It could be a CC, or it could be something like an RC to a 1O, and then a C, like this. Also, be wary that the bold carbon means the carbon that's being picked. This carbon's being picked up, not that one. Right? Those are our options. We might need to narrow it down further, but the other ones will help us figure that out. So we've got a peak at around what 75 ppm now. Here, if you look at our data sheet, what lies in the range of 75? So that one is a carbon here with bonded to an oxygen like that, right? So that could be an alcohol, it could be an ester or an ether, any one of them. Fine. Now we have another peak at around what 210 ppm. If you look at our data sheet, what falls in the 210 range? It's aldehydes or ketones. So we've got an R, we've got a C here. Again, I'm making it bold on purpose, and a double bond O there, and so forth. And it's this carbon being picked up. Fine. Then, not really helping us figure out what's going on here. What we know is that we've got a C double bond O, we've got a COH. Fine. Next, let's look at our proton NMR spectrum. Obvious, first thing off the bat is we know that there's 1, 2, 3, 4 overall groups of peaks. So 4 peaks means that there's 4 hydrogen environments. Okay, so we got a peak at 3.9 ppm. Now, if you look at the data sheet, I'll copy and paste it here so you can see. Okay, so if we look at this first peak at 3.9 ppm. Now, this 3.9 ppm could be this, it could be this, it could be this, it could be this. But from before, we need to remember that we picked up that it has a C double bond O that's not part of a carboxylic acid. It's either an aldehyde or a ketone. And we know there's an OH from an alcohol. So some of these can be knocked out. So for example, that ester's gone. And that carboxylic acid's probably gone. Out of the ones left that it probably is, this one's a bit too variable. And also, if we think about it, there's it's a quartet. So the adjacent carbon must have 3 hydrogens. And its integration is 1. So if we picked ROH, then that means, yes, it fits the integration of 1 here. But then its adjacent carbon would just be 1, 2, 3, and that's it. It's the molecule done. It's methanol. So it's not going to be that one for this peak. So the only other one it can be is here. So it's 3.9 ppm. So it suggests that you've got a C with this H being picked up by the spectrometer. It's a quartet, so the adjacent carbon has 3 hydrogens like this. And its integration is 1, meaning this carbon has 1 hydrogen on it. And there's an O here, and then something else on the other side of it, like that. So that's the first piece. Then if we look at the second one, so 3.7 ppm, it's a singlet. So the adjacent carbon has 1 hydrogen. So 0 hydrogens, whoops. And its integration is 1. So we need to now look at this and think what this could possibly be. So again, it's, let's see. it's probably not going to refer to this one because that's again talking about that carbon there. And there's no this doesn't count as its adjacent sorry, not that one, I'm pointing wrong thing. It's probably not this one because it says that its adjacent carbon would have 0 hydrogen. So it'd be another carbon with absolutely none of these being hydrogen. And its integration is 1, which fits that. So I think which would fit that, but again it wouldn't work out because then it would just be mirror that with extra like bits of carbon on, like with extra stuff there that doesn't have enough space for like, you know, carbons bonded without hydrogens, which means it wouldn't work if you tried it. So this one, this 3.7 ppm, is probably that there because it's an integration of 1, which fits the OH there because there's 1 there, and its adjacent carbon has 0 hydrogens. So that's still possible because then that means that R group, so it would be COH like this. This carbon's probably bonded to other stuff like maybe other carbons or so forth. So maybe it's probably that, more likely that one. 2.1 ppm. So it's a singlet. So its adjacent carbon has 0 H's as well, but its integration is 3. So there's 3 hydrogens or whatever one this one is being that's picked up. So if we look at what that one's going to be, the 2.1 ppm, let's look at the ranges. It's probably going to be that. So because it's this carbon's hydrogen that's being picked up, the integration applies to this carbon. So what we have is we've got CH3 like this. We've got a C double bond O there. And then we've got something else here. And that fits because this carbon has no hydrogens on it because this is the adjacent carbons. So then we have the 1.2 ppm peak. 1.2 ppm. I think it was a doublet. Yeah, doublet. So the adjacent carbon has what? Has 1 hydrogen. Sorry. And it's an integration of 3. So then we need to figure out what that one is. Well, what fits that range of 1.2 ppm that would probably be realistic? Either that or that. And that's about it, to be honest. It's probably just a bunch of methyl things going on here. So the 1.2 one, so that's R, C, and then it's integration of 3. So H, H, H. And it's told you that it is a doublet, so its adjacent carbon has 1 hydrogen. So that means that R group there is going to be a C and an H. So now collect all the pieces of the puzzle that you've got together. So we know that, again, it has to have a COH that's an alcohol. We know its empirical formula is C2H4O. We know that it has 4 hydrogen and 4 carbon environments. And we've got some puzzle pieces here. So we know that one of the pieces of this puzzle is an OCHCH3 like this. We know that another puzzle piece is going to be a C, O, and an H like that. And then we know another piece of the puzzle is going to be this C double bond O and a CH3 like this. And then another piece we know is going to be CHCH3 like that. Which you can see is matching because we can see there's a CH and CH3 here and then there's one there. So probably what we've got in this is we've probably got, you know, your CH3 is sort of, you probably got like a C and an H here, and then your CH3 definitely is probably part of that molecule, right? And then if you compare that to that, we can see that this carbon is also bonded to an oxygen, so we probably have an O and an H here. But remember that this one only has 1 hydrogen, so this is probably stuck to another carbon of some sort. So let's look at the rest of the pieces that we've got left. So this would address that one, and that piece, and that piece. All that's left is this piece. That carbon is probably stuck to this one here. Because, again, that remember, from all these pieces, this carbon can only have 1 hydrogen, so it can't stick any more hydrogens on. So it's probably a C double bond O here, then a CH3 like this. So if we tidy this up and make it look a little bit prettier, we would have CH3 like so, C double bond O, and then a COH, and then a, sorry, there's an H there as well, sorry, and a CH3. So that's 1, 2, 3, 4. So that's 4 carbons. Then we have 1, 2, 3, 4, 5, 6, 7, 8. So that's C4H8O2, which if you half it gives you C2H4O. So we're nearly there. All we got to do is just check it fits the 4 carbon and the 4 hydrogen environments. So all you do is you just look at them and see how symmetrical it is. So we've got 1 carbon here. This is a different carbon. That's a different carbon. And that's not the same as the other one because that one's next to an OH and that one's next to an O, and they're also different distances apart. So we've definitely got Sorry, we rubbed the hydrogen out. So we definitely have 4 carbon environments. And if you look at the hydrogens as well, here's 1, there's 2, there's 3. Whoops, sorry, there's 3 because they're all these 3 are on the same one, and there's 1, 4. So we've got 4 hydrogen environments, and there you go, done. So this question's about esters, and it shows you an incomplete mechanism for the reaction with an ester with an aqueous sodium hydroxide. What I see people say is they're like, I've never done this mechanism before, I don't know what the curly arrows are for it. Like, it's not that you're not supposed to know the mechanism for this. This is, the whole point is it's testing your skills of being able to know how to draw the curly arrows and what might be going on. Which is why, I think I said before, it's really important to know what's happening in terms of electron movement when you're drawing curly arrows and what's going on. Because they do this. They give you unfamiliar mechanisms and they're like, all right, go and draw the arrows, lad, and do it. So if we have a look here, they've started us off. They said the lone pair of this oxygen is being passed on to this carbon here, like that. So what's happening is this pair of electrons is being donated to that carbon. That oxygen is acting as a nucleophile, an electron pair donor. So then if we look here, what's going on is that OH is now stuck there, which makes sense because it's just done that. But this carbon now has too many bonds. It has a 1, 2, 3, and what would have been 4 and 5, because remember there's C double bond O there, right? So how on earth has that C double bond O just become this with an O minus? This O minus has now gained an extra pair of electrons from somewhere and has become negative, and that bond has now become a single from a double. So what's happened is that some electrons from here must have been passed on to that oxygen like that, and that bond is broken. So it's important to understand which way things are moving. Right? Compare side by side. So if we compare side by side, this bit's dealt with because now we have an OH stuck on it. That's fine. And now this would give this oxygen a negative charge and a lone pair of electrons, and this double bond would have been broken, which is what we've dealt with here. So between this first and second step, there's not much more needing doing in arrows-wise on this. So let's look at the next bits then. So what's going on between this and the next one? So we're happy with the CH3, but if we look here, we've got a COCH3, but it's gone. That C double bond O is from here. So this thing has been booted off. So we need to figure out which way the electrons are going. So remember, this is a covalent bond here between the carbon and oxygen, and it's broken. We need to figure out which way is it going. If it's passed on to here like that, then this carbon would have too many electrons and it would be negative. So it's being booted this way to kick it off. So that oxygen is now negatively charged, like that. That would get us to this point here where we're happy, because now we've got that double bond remade here. And we've kicked off the OCH3, and we can look at the next. Oh, actually, it's right here, the COH3 we just did. So this COH3, what it's doing is that this electron pair is being given to the hydrogen. But that means that hydrogen would have 2 covalent bonds, and it doesn't like doing that. It's too many bonds. So it's got to get rid of electrons somehow, the extra ones. So what it does is this bond breaks, and it passes the electrons onto that oxygen, like that. Which is where, whoops, that makes sense now, because you can see that the CH3O minus with the H has now become that. So it's good. And it makes sense here now that we have this negative charge. So again, they love doing unfamiliar mechanisms like that to test your skills on being able to know what the curly arrows actually mean and what's going on. Single bond means you have a pair of electrons shared because it's a covalent bond. Double bond means you have 2 pairs, so 4 electrons. So then it says, name the type of reaction shown in figure 4. So it's told you that they're reacting an ester with an aqueous sodium hydroxide. So what we make here, we've made a carboxylate ion, because that is, remember, that looks like the derivative of a COH, C double bond O, carboxylic acid. It's just lost the H now. And that is an alcohol. So this one has to be base hydrolysis. If it was acid hydrolysis, you would just make that again. So this is base hydrolysis of esters. So then it says, deduce the role of the CH3O minus ion in step 3 as shown. So look at what's happening between them. So let me just rub that bit out, sorry. We've got CH3O minus. So we start with CH3O minus. And then at the end, we magically become CH3OH. Compare side by side, what's it gained? It has gained an H+. That is also known as a proton. This is bonded with a proton. It has taken a proton. It has accepted a proton. When something accepts protons, it is known as a base. So people love saying proton donor, proton acceptor. Like, they don't actually realize that that means it's binding with an H+. If I have HCl, and although its equilibrium is so far to the right, it is still technically reversible. And if I have H+ and Cl minus, and acid is a proton donor, meaning it donates, it gives away, it loses H+, so that's your acid. But a base is anything that can gain a proton or accept it or gain an H plus or react, take an H plus on. So technically, that is a base because this base can react with this H plus to give you that again. So it acts objectively as a base. So long as you're accepting an H plus or a proton, you have a base there. A triester in vegetable oil reacts with sodium hydroxide in a similar way. What's a use for the product of this reaction? So what you end up making is you make a carboxylate salt. And when you have a sodium carboxylate salt from this, it's actually used in soaps. So you made a soap. So now it says benzene reacts with methanol chloride in the presence of a catalyst. So you should be able to recognize, obviously, benzene, but that is an acyl chloride, which looks like a C double bond O Cl like that. You should be able to see this and be like, oh, that's what it's going to look like. So then you should be like, okay, what do I know of where benzene reacts with an acyl chloride? And it's like, oh, that's what it is. We're doing Friedel-Crafts acylation, all right? So it says, give an equation for the overall reaction when benzene reacts with methanol chloride. So we start with, well, think about what you start with and what you finish with, right? So we know that they're reacting benzene to C6H6 and this methanol chloride, which is HCOCl. Then think, okay, well, what would this make? So what happens here is you've got electrophilic substitution because one of the hydrogens gets swapped for some part of this, right? So this hydrogen gets knocked off. So then think about what happens. One of these hydrogens gets swapped for the electrophile that comes out of this. The end product doesn't have a Cl in it. That Cl's not taken off, and that's what generates your electrophile. So what you end up with is you've got C6H5, because one of them's been substituted, with the rest of this thing without the Cl in it. So CHO. So then you need to think, well, what have I got left over, and what do they react to make? Because remember, you have to have all your atoms in your chemical reaction. So we lost an H from here, we lost a Cl from there, so the other product is HCl. So that's that. The name of this then, so you've got a benzene here, and then you've got a C double bond O and an H. So you need to be able to recognize what that looks like. So you got a benzene, and this group here, what's that called? Give yourself a second to think about it. So it's an aldehyde. So this thing, the only way you can name this is probably going to be benzaldehyde. There's not really any other way you can say that. Benzaldehyde. Because, for example, if you said like benzene methanol or something like that, it don't make sense. Unfortunately, sometimes if you can't think of a name like that, it's probably going to be that. So then it says, identify the catalyst needed in this reaction, and then give an equation to show how this catalyst is used to form the electrophile. So they've even told you what the electrophile is. How lovely of them. You need a halogen carrier catalyst, so AlCl3. It can also be AlBr3. It can be literally any of them. So they've told you that they were making the electrophile here, right? So look, even if you don't have to memorize the equation, you can just work off of what's in front of you. They've told you go from that, and it eventually sticks onto that, but they've told you in the middle you're making an electrophile. So we start with HCOCl, and then just use what they've told you. You're going to make HCO+. Okay? And then they've told you that we're using this catalyst. Well, I mean, they haven't told you, but like where we need to recognize that as the catalyst. So we're going to put plus AlCl3 here. Compare them side to side. What's going on here? So this is an HCO with a Cl on it. And now it doesn't have a Cl anymore, and it's become positive. This Cl bond has broken, and the electrons in that bond must have gone to the Cl, because otherwise it wouldn't be positive. You'd have a radical instead. So if that's the case, then this thing's got extra electrons, and it's bonded to this, so you actually make AlCl4-. That's why. So then it says, outline the mechanism of the reaction of benzene with this electrophile. So you've got your benzene here, you got your lovely ring there, and here's our electrophile. So we've got C double bond O and an H. Remember, this is now positive because it's missing that the electrons from that bond that it once had with chlorine. And now think carefully what you're doing with your arrows. This thing wants electrons, and it's an electrophile, so it's an electron pair acceptor. So it's going to go for something that's rich in electrons. So normally, you guys are familiar with electrophilic addition. That's the rich electron source. In this case, it is the benzene ring. It's the pi system here that donates electrons like that. Then what happens is you've got your benzene here now, but now you've got H here, and you've got a C, H, and a double bond O there. But there's too many bonds here because you've just given electrons away to this carbon, and it's positive, it's broken. And you need to make sure that this broken ring really points at that like that. That's the mechanism of the reaction. But then also, we need to fix this ring again, and we need to get rid of the too many bonds around here. So what happens is that this hydrogen has to break its bond and give electrons back into the ring like that. And then it regenerates the ring, like so. And then you've got your new C double bond OH stuck on there like that. And that is an electrophile that has substituted for the H. This question's about olive oil. A sample of olive oil is mainly the unsaturated fat Y mixed with a sample of inert impurity. The structure of Y in olive oil is shown, and it has the molecular formula C57H100O6, and its MR is 880. The amount of oil is used by measuring how much bromine water is decolorized by a sample of oil using this method. Transfer a weighted sample of oil to a 250 centimeters cubed volumetric flask and make up to the mark with an organic solvent. So they got 250 centimeters cubed of oil. And what did they do? They took 25 centimeters cubed out and did what with it? Titrated 25 centimeters cubed sample oil solution with. So they, and don't say titrated with, make sure you clearly understand what's going on here. They reacted it with 0.025 mol dm minus 3 br2, right? Because now you really understand what's going on here. A suitable target titer for the titration of this is about 30. So roughly they're aiming for using 30 centimeters cubed of this. Now it says justify why a much smaller titer would not be a good idea. So you're thinking in terms of practical stuff here. What's the why do we ideally want to use gigantic measurements? So imagine if you're measuring this to a centimeter cubed, you're adding plus or minus 1 centimeter cubed uncertainty onto every measurement you ever take. 1 over, let's say we take 2, that's a 50% percentage uncertainty. 1 over 200 is a 20 is a 5% one. 1 over 200 is a 0.5% one. And so forth. Like, the bigger the quantity is, the smaller your uncertainty tends to be because of the fact that it's just 1 or plus or minus 1 centimeter out of like 200 centimeters cubed. It's going to have a pretty small impact. So here, smaller, tighter increases percentage uncertainty. And this applies to every single experiment you'll ever do. Then what it does is it says calculate the amount of moles of bromine in the target titer. So the amount of Br2 is going to equal, so its concentration 0.025 mol dm minus 3 times its volume over 1,000, which is 7.5 times 10. Now it says calculate a suitable mass of olive oil to transfer to the volumetric flask using your answer to 0.91.1 and the structure of Y. Then assume that it contains that much by mass. So I've actually just crossed it out, like rubbed it out, whoops. But what they've done is they've put 250 centimeters cubed of like an oil plus water mixture. So what they've done is they've taken this and they've added it up. It's a mixture, I should say. Then what they did is they took 25 centimeters cubed and reacted it with what? Don't just say titrated with. Say to yourself that you know these two are reacting with each other. So Br2. Now we know that the concentration of this was 0.025, and we know that its volume that we're aiming for is 30 centimeters cubed, right? Now the question, what do they actually want you to find out? So they said calculate the mass of oil to put in flask, right? And then they said that of this oil, 85% of this is Y. So it's not that Y doesn't make the full 100% of it. Now you can work backwards. You should be able to recognize that we know that this mysterious stuff, whatever it is reacting with Br2, and we know its concentration and volume, and we know it's made of. We took 25 centimeters cubed, so 250 will have 10 times as much. And then within this mixture, 85% of it is Y. So now we can work backwards. All we need to do is we need to write an equation to figure out what this oil mixture thing is. So this oil mixture that's got Y in it, we need to figure out what parts actually react with the bromine. What's going to react with the bromine? Well, look at the diagram here. Have a think and then tell me what you think, because I'm going to sneeze. So the actual bit that's doing the reacting, there's alkene groups here. So 1, 2, 3, 4, 5. So there's 5 alkene groups. So if you add Br2 to every alkene group, you're going to get rid of 1 each time. So because there's 5 of them, it's going to be a 1-to-5 ratio of these two. Right? So Br2 reacts and makes a halogenoalkene, whatever, right? So we know, and we worked from the previous question as well, that we know that the moles of Br2, and remember, write down the moles of what it is and where it sits in this thing. We worked it out from before, was 7.5 times 10 to the minus 4. Therefore, the moles of this oil, because it's a 1 to 5 ratio, because we just figured that out, is going to be 7.5 times 10 to the minus 4 divided by 5, which is going to be 1.5 times 10 to the minus 4 moles. But then remember, where is this number coming from? What does it apply to? We know that it's 25 centimeters cubed reacted with this Br2. Then we know that that's how many moles we're going to expect. So therefore, in 250 centimeters cubed, because remember, we took a 25 centimeter cubed sample out, it's going to equal that times 10. So it's going to be 1.5 times 10 to the minus 3 moles of this stuff. Now, because we're working with the oil reacting the Br2, the actual bit within the oil that's doing the reacting is Y. So therefore, the actual moles of Y that's doing the reactioning part, because they've told you in the question it's an inert substance it's mixed with, is minus 10 to the 1.5 times 10 to the minus 3 moles. Therefore, we can work out the mass of Y in this 250 centimeter cube sample because they've told you what the MR is. So it'd be 1.5 times 10 to the minus 3 times 880, which is going to be 1.5 times 10 to the minus 3 times 880, which is going to be 1.32 grams, right? But then they've told you, they want the mass of the oil. They've told you that 85% of the oil is Y. Therefore, Y equals 0.85 times the mass of the oil. So to get the mass of the oil, sorry, and that's 1.32 grams. To get the mass of the oil, all you do is you do 1.32 divided by 0.85, sorry. And that will give you the actual mass of the whole oil, including it. So that's 1.32 divided by 0.85, and that gives you 1.55 grams. In these questions, I just see people mindlessly just working out routines and moles and this and that. It just does not work. You have to understand what you're working out this for, why you're doing it, and what you're going to do with it next. So every time you're doing any chemistry calculation and it's like step-by-step problem solving bits like this, think, what am I going to do with this directly after I work it out? If you can't justify it, then you don't know what you're doing. So now it says the olive oil solution can be prepared using this method. Place a weighing bottle on a balance, record the mass to 2 decimal places in grams, and then add olive oil to it until suitable mass has been added. Record the mass of the weighing bottle in the olive oil. Pour the olive oil into this flask. Add organic solvent to the flask until it's made up to the mark, and then add a stopper and then invert it several times. Suggest an extra step to ensure that the mass of olive oil in solution is recorded accurately. So what could you do? Well, what they've done is they've put oil in they've got a weighing bottle, they put oil in it, and now they've poured it out. They weighed the mass of just this thing on its own without oil in it, but some oil might still be stuck in there. So what you should do is you should weigh the bottle after transferring oil, and then why some oil might be left behind, or so not all of it will have been transferred. And then it says suggest the reason for inverting the flask. The reason we do that is to ensure it's mixed evenly or it's homogeneous. You can use either. It's so that, because if everything just settles at the bottom, then if we take a 250 centimeter cube sample from here, that's like not 25 centimeter cube, sorry, sample from here, that's useless. But if it's all spread out really nice and evenly, as best I can do that, then if you take 25 centimeters cubed out, you can assume that the original thing had 10 times that, if it's all spread out nicely. So a sample of the olive oil was dissolved in methanol and placed in a mass spectrometer. The sample was ionized using electrospray ionization. Each molecule gained an H plus ion during this. The spectrum showed a peak for an ion of MZ345 from the vanilla purity of this olive oil. The ion with the MZ of 345 is formed from a compound with an empirical formula of that. Deduce the molecular formula of this compound. So all they've told you is that the empirical formula of this mysterious thing has C5H10O, and we know that this MZ peak we see is 345, right? But they've told you that in this question that every single one of these has gained an H plus. So its actual MR is going to be, well, you got to take the H plus off, so it's going to be 345 minus the mass of H plus, which is just 1. So its actual MR is 344. Now, if you look at, now to actually figure out what its formula is, well, you just work out the MR of the C5H10O, because that's its empirical formula. That's going to be 12 lots of 5 plus 10 plus 16, which is 86. And then you just do 344 divided by 86, and that'll tell you how many multiples of that we get to the original thing. So 344 over that is 4. So that means that the empirical formula that we have is, to get to the molecular form, the original form, you got to times it by 4. It's 4 times less. So that means it would be C20H40O4. Read the question. You have to do any. Sorry, whoops, O4. You just got to read the question. It's all there for you, You just got to look with what they say and then work with what they say. So now it says, it's a reaction scheme here of what's going on, and it says, what are the reagents needed for step 1 and then the reagents needed for step 2. So it says state the reagents needed for step 1 and reagents needed for step 2. So when it says reagents, it means what are you going to put in this thing in the lab to make this reaction happen, right? So that includes things like catalysts. That includes things like, the actual substance you're putting in. So if we look at step 1, what we do, we've got a methyl group here, and then we've got an NO2 here. So whatever's happening between these two groups, NO2 is being added on. Now you should be able to recognize that that's an electrophilic substitution reaction. The reagents you need to make that happen is going to be HNO3. But as well as that, it won't happen unless you generate an electrophile using that, and it should be concentrated, sorry, I should say. You should also be using concentrated H2SO4. Because those are reagents to let this reaction happen. Otherwise, it won't happen. Now, step 2 is we've got the NO2 and it becomes an NH2, right? So it's been reduced. So the reduction of this part is there's two options. Either it's SN and HCl, or it could be nickel and H2. Either's fine. So then it says, suggest the name of the mechanism of the reaction in step 3. So if you look at step 3, what's going on here? We have an NH2, and now there's a COCH3 stuck on it. So you need to figure out what we're going from an amine to what looks like an NHC double bond O, and so forth. So that's an amide. So you need to think how on earth you can go from amine to amide. So what was originally used here, you should be able to recognize, was an acyl chloride. So you must have had a C double bond O and a Cl there, and then a C, the rest of it. And that Cl is gone, and has instead, this carbon's now bonded with the nitrogen here, right? So the mechanism for that, well, you need to think, why is that nitrogen bonded here? Because it's got a lone pair of electrons. It's ready to donate those electrons to this carbon that's losing its chlorine. So it's got to be a nucleophilic reaction. Next is, well, you're adding this thing on. So it's addition. But we've lost an H from here, and we've lost a Cl from there. So we've eliminated as well. We've kicked something off. So it's a nucleophilic addition elimination. Then it says, name the reagent for step 4, and then state a necessary condition. So step 4, what have we gone from? We've gone from a CH3, an alkene, to a halogenoalkane. So it's really important you recognize that it does not matter if it's stuck to a benzene. As long as it's there, it will probably do the same stuff. So alkenes to haloalkanes, you should recognize free radical substitution. So the reagent you're going to need is something to provide the chlorines. So it's going to be Cl2. And then as well as that, the condition for this to happen is you're going to need UV light. So then it says, amine A is formed in step 2 and amine B is formed in step 5. Explain why the yield of B in step 5 is less than A in step 2. So let's see what we got going on here. So what it's saying is why on earth are you making less B versus A? So compare them side. I realized that it didn't record the last part of this, which is really annoying. So what I was saying is it says explain amine to A is formed in step 2 and B is formed in step 5. Explain why the yield in B is less than A. Sorry. So what we can see here is that we've got an alkene group attached to a Cl. So that's a haloalkane bit, and that's been swapped, the Cl, for an NH2, meaning that there is nucleophilic substitution going on. When you have nucleophilic substitution and you're going to an amine, for as long as that amine has lone pairs of electrons on it, it will carry on and be able to do more. So what happens is this B actually drops down because you've got more substitutions and extra byproducts. Whereas here, all you're doing is reducing the NO2 into H2. So that cannot make like any other possible product if you do it right. So therefore, step 2 only produces amine A, whereas step 5B could have more substitutions. So next, explain why amine B is a stronger base than A. So I've drawn them side by side here. So A has the amino bit stuck to an alkyl group on the benzene, whereas B has it directly stuck to the benzene. So when you're accepting a proton, everyone loves to just say, oh, acids are proton donators and bases are proton acceptors. What does that actually mean? It means that acids lose H+, bases gain H+. Now, any acid in the universe will have a reversible dissociation. Hydrochloric acid's just so strong it's almost to the right. But if we look at hydrochloric acid, for example, this has lost an H+. Therefore, by definition, it is an acid. Whereas this can gain H+ to form HCl. So that is a base. So whenever you have anything where it can give out an H+, it is an acid. Anything that bonds to an H+, is a base. Don't just memorize proton, donor, and acceptor. Why am I saying all that then? So, when you have amines, they can act. When you have amines, they can act as bases because they can bond with a proton by forming a dative covalent bond like so. For as long as there's a lone pair of electrons on that amine, it can do that. So the reason that this is relevant is because the way I think of it is that benzene loves electrons. Sorry, benzene loves electrons. It's like, yeah, I want all of them. So it kind of pulls them to itself, these lone pairs here. If they're being pulled towards the benzene ring, that means it's less available for this H+. It's not going to strongly bond to the H+, meaning that it's going to form a bond with the H+ less. I mean, it's a weaker base. Whereas here, this this amine group is not attached directly to the benzene ring and is instead has another alkyl group. So these alkyl groups are hell electrons. There's a pair here, there's a pair here, there's a pair here. So all of these electrons, I like to think of it as they push on those electrons here, the lone pair, because remember electrons repel, and it repels across the entire molecule because they're all right near each other. And what happens is it almost pushes them straight towards the H+. So they are more available, more ready to give on to that H+, meaning that this is more available. So what you would write here is exactly that, just in words. So in B, the alkyl groups can push electrons on the nitrogen, the lone pair I should say, to the H+, and these electrons are therefore more available. That's known as the positive inductive effect. You can't just say positive inductive effect and not explain what it means. You don't get any marks, so don't do that. Anyway, I hope that helps. I'm going to upload lots more, and please like, share, subscribe with your friends.